Hello everyone, my name is Entropy Xu. I'm currently a postdoctoral researcher at the Hong Kong University of Science and Technology. So today I want to give everyone an overview of my work called LLM.265. And this work project was completed during my time at Duke University, guided by Professor Lisa Wu-Wells. And this was a collaboration with the Carnegie Mellon University. And in this work, we demonstrate an interesting phenomenon such that for a video codec, although it is originally designed to compress video footages, the video codecs, such as H.265, actually achieves the state-of-the-art information efficiency when being used to compress tensors. So we will go over why do we even thinking of the video codecs in the first place. Then I will provide some explanations for why that works at all, and then I will present some experimental results. At the end, I will summarize the unique features provided by codecs, including being general purpose, versatile, and efficient in terms of both information and hardware. And of course, we will discuss the insights that video codecs have provided for future architecture designs. So first, let's talk about the motivation and background of this research. Why are we even thinking of video codecs in the first place? So everyone knows that GPUs are pretty busy when running large language model workloads. And when we look at the die of a GPU, we can find several components. And we know that all these components, such as the CUDA cores, the on-chip network, and the memories are being saturated during inference and training. But there is one small component, we find it idle the whole time, and that's the video encoding engine, which is composed of encoding and decoding pipelines of video codecs. And such phenomena leads us to think, since we got that for free, can we make it any useful? But before we show you the usefulness of video codecs, I want to give you a little bit more context about exactly what's being involved in a large language model training and inference. So here we have one GPU, and the basic is that for inference, the weights and the KB cache inside the memory of are need to be stored inside the memory of the GPU. And for training, we also have to maintain the gradient as well as have some rooms for the optimizer states. But one GPU often isn't enough, and we usually have a data center of GPUs to parallelize and accelerate the computation. So suppose we have 4 GPUs here. In the most basic setup, we split the model across 2 dimensions by data parallelism and pipeline parallelism. However, this requires the communication between GPUs, which can be expensive in terms of performance, hardware cost, and energy. And in this example, we have 2 data parallel rings and 2 pipeline parallel rings, which means that we must transfer activation between pipeline stages, and if we are doing training, we also have to backpropagate the gradient and gather the weight gradient after each training step. And even in such a small setup, we have to communicate both horizontally and vertically. To make this clear, the data communication at each step includes the activation for each and every token at every layer, as well as the weight gradient of the entire model. And when we scale to a data center with thousands of GPUs and scale to models with hundreds of billions of parameters, such communication can become a major bottleneck. Therefore, the logical next step is to explore compressing this data directly to reduce its footprint and alleviate these bottlenecks. And plenty of researchers have been done on this topic. However, most of the existing approaches only focuses on a subset of the whole spectrum. For example, we have GPTQ, AWQ doing weight-only compression. We have the Quarot and the QServe that extend this compression to KB cache. And we also have the 1-bit series of optimizers like the 1-bit Atom and the 1-bit Lamp. But one great thing of our LLM.265 is its generalizability, such that it works for all types of tensors, which means that we only have to maintain one software stack to compress everything, which greatly simplifies the system design. And in addition, our method also achieves better information efficiency compared to existing works that's specifically designed to one or two types of tensors. And such that our method can compress the model to be a smaller number of bits while allowing the same or even better model level accuracy. And after we have discussed this, one thing that comes to our mind is why video codecs work at all. Why does something that's originally designed to compress video footages work for tensor that seems totally unrelated? So video codecs are extremely complicated monsters taking decades for humans to finalize. So here, I can only give you a very simplified version of it as a background, but you can always refer to our paper for more details. So for a video codec, the input is raw video frames and the output is a compressed bitstream. And there are multiple stages of pipeline that connects the input to the output. So one stage is the CPU partitioning that smartly partitions the frames into micro blocks. And after that, we have a JPEG-like transform and quantization pipeline that serves as the backbone of the codec. What's making video codec stand out from a typical JPEG compression is the prediction stages it contains. And basically, the idea is that if you can predict, then you don't have to store everything. And two levels of predictions are being explored. The intra-frame prediction works for pixels that can be predicted within the frame. And we also have the inter-frame prediction and the motion estimation, which works in a similar fashion, but pays more attention to the pixels that can be predicted from adjacent frames. So let's do a quick test to see if the video compression works. Say that we have a sample tensor sampled from the llama model's weight, and it is quantized to 8-bit integers first. And let me define the rules here. So we will be gradually adding compression stages from the video codec to form a pipeline. And some of these stages is lossless, and some of them is lossy. And our rule is that the mean square error, the MSE of the compressed result, should be within 0.1 from the original raw format. And we will show the minimum number of bits per element that a certain pipeline takes to achieve such goal. And basically, with this setup, the lower number of bits to store the same amount of information, the higher the information efficiency of that certain pipeline. Okay, so let's start adding stages. We first add the entropy coding stage. And in this stage, the average bit width per element is reduced from 8 bits to 7.6 bits. And because with entropy coding, you can remove some redundancies in the distribution of symbols. Then we add the DCT transform stage, and this is when the compression becomes lossy. And because it is lossy, we have plenty of gains in reducing the bit width from 7.6 bits to 3.5 bits per element. And then we have the intra-frame prediction coming in, which gives us another gain of 0.6 bits per element. And after that, adding the CTU partitioning gives us another gain of 0.3 bits. And unfortunately, that's where things stopped. And if we add the inter-frame prediction and motion estimation into the pipeline, not only do we not see any gain, the information efficiency even getting worse, showing that the inter-frame prediction and the motion estimation does not work for tensor compression. So we showed an overview of how each stage contributes to the compressibility of tensors. Let me give you two more concrete examples. And this first example is about why DCT transform work. So let's look at the distribution of values in large language model workloads. And typically, as plenty of researchers have shown, this distribution resembles a normal curve centered at 0, but with long-tail outliers on both sides. And prior works have consistently observed this pattern in the distribution of weights, activations, and also other types of tensors. And these outliers are problematic for quantization and compression algorithms because they have a high variance and they occur sparsely, which makes them hard to encode. And video codecs address this issue using a step called the discrete cosine transform. And on the right side, we can see after the DCT transform, the outliers have been removed, resulting in a clean and smooth distribution. And let's look at another example of one small block of values at the bottom left of the page. And we can see that an outlier with value of 128, and this outliers just disappears after we have applied the DCT. And we can verify the result on the right side that the block no longer contains any outliers. And essentially, what the DCT does is that it migrates the encoding difficulties from the outlier to adjacent positions within a block. As a result, the transformed data is much easier to quantize and much easier to encode compared with raw values. And another example why video codecs works for tensor is a little bit more tricky, but also more effective than the previous one. And let's take a look at the block of values from the weight tensor in a llama model. And if we look closely, we can observe horizontal patterns like lines in the tensor. And this happens because each row in the block represents the weight within the same neural network channel, and prior studies have also shown that values within the same channel tends to have similar scales and varies only slightly. And this phenomenon is often called the channel-wise distribution in neural network models. What's coincidental is that video codecs are specifically designed to compress images that show similar patterns to tensors. For example, the image often have lines or regions with continuous colors, and video codecs are optimized to encode these patterns with intra-frame prediction. For instance, if an edge is detected, instead of encoding all the values in a row numerically, the video codec can just represent it as, well, there is an edge with black value at the 7th row. And this will save a significant amount of storage space compared to encoding each individual pixels. And in most of the cases, the intra-frame prediction is not perfect and usually leaves some residuals to encode, but that's okay because after the prediction, the residuals are much smaller in scale and much easier to compress compared to the raw values. And okay, great, it's finally time to show some real result about using video codecs to compress large language models. As we have mentioned earlier, LLM.265 works for various types of tensors, and let's begin with the model weight quantization and compression. And here, our method is evaluated along other compression approaches, including the GPTQ and AWQ. The result for our so let's first take a look at the PIQA dataset. So the x-axis is the average bit width per element, and the y-axis is the evaluation accuracy. And from these curves, we can see that our method achieves excellent accuracy retention even at lower bit widths, so that accuracy comparable to the 4.25 bits baseline from the GPTQ and AWQ, but our method only requires 2.65 bits per element, showcasing our method's exceptional information efficiency. So one unique feature of the video codec here is that it got versatile bitrate, which means that this allows us to have a fine-grained control on the storage budget. While existing method almost always relies on quantization into integer number of bits, but for our LLM.265, we can set a fractional bitrate. It could be 2.265 bits per element, or 3.1415 bits per element, or any real number. And such versatility enables us to have a finer grain control over the trade-offs between the accuracy and the footprint. More importantly, related works like GPTQ and AWQ all requires input data-aware calibration, which means that a carefully chosen dataset needs to be used to calibrate the quantization and compression process, making the quality of the compressed model data-dependent and fragile to the change in input distribution. But also, our method is purely data-independent, making it more robust and easier to deploy. And you can, so we have talked about compressing the weights. How about compressing the activation and the KV cache? It turns out that our video codec achieves the state-of-the-art information efficiency for KV cache and activation compression, and we have compared our approach with other state-of-the-art schemes such as the Poirot, SpinQuant, and run it to nearest in the figure at the right side of the page. And from this figure, it shows that our method achieves the best accuracy among all these existing works. And being able to compress the KV cache is extremely helpful in a distributed inference setting, as the communication size between pipelines can be greatly reduced. And more importantly, if we still remember from the original die shot, that the video codec is hardware accelerated, and this makes the communication compression between GPUs for a distributed inference setting even more efficient. And after testing the inference, we have also modified the deep speed framework to test our video codec on distributed training setting. Like we have talked about before, there are pipeline parallel training and data parallel training. So for the time's sake, we will only be looking at the data parallel training here. You can always refer to our paper for more details about pipeline parallel training. So for data parallel training, it requires us to compress the weight gradient across GPUs. Here, we train the PyCR 0.5 billion model on 4 GPUs with weight gradient compression enabled, and this plot shows the convergence curve for the training setting. And we also compare our method with other compression baselines, such as the 1-bit addon and the 1-bit lamb method. And our result shows that while baseline compression method requires 3.3 bits, our method achieves better accuracy, better convergence than baseline, requiring only 1.4 bits per element. And this is very surprising information efficiency, as that even if we compare with the uncompressed baseline, if we want to maintain a comparable convergence rate with the uncompressed baseline, our method only requires 2.6 bits per element, and this leads to more than 6 times compression ratio compared with the original 16-bit floating point numbers. At the end, I would like to present some results and some insights we got from our work. As computer architects, we must now be very curious about the hardware cost of the codec. So let's compare it with other devices in large language model infrastructure. First, this is the die of an RTX 3090 GPU with a die size of over 600. And here's the die of the Mellanox CX5 network interface card with die area of 170. And comparing with them, here's the die area of the video encoder and video decoder, all scaled to have a total throughput of 100 gigabits per second. And both their area is below 1 millimeter square, which is only a small fraction of the die area of other devices. And furthermore, when we look inside the video codec, we see that the majority of the die area of a video codec is spent on the interframe prediction. And recall back from our very early slide that interframe prediction only works for videos and does not work for tensor compression. So in theory, we can remove these portions to make the codec even more smaller and even more energy efficient. And I think that leads to a straightforward question that, can we modify the codec to do anything better? And based on our observation, our proposal here is a new design called the Trinity codec, which merges the compression pipeline of tensor, video, and data into one pipeline. And inside is that these three compression pipelines shares many common stages, and reusing hardware is always beneficial. Going into more details of this Trinity codec, we know that the interframe prediction does not work for tensor, and we know that there is an upper limit of the demand for video encoding and decoding. And given that, our design decides to augment the tensor required pipeline for throughput while leaving the video-specific pipeline stages minimum. And notice that this is much better than simply duplicating the video codecs, because now we only need to augment the stages that works only for tensors, which makes the whole implementation more efficient. At the end, we simulate and evaluate our approach in a large distributed training infrastructure. The result shows that as the model size gets larger and larger, and when the dataset size scale gets larger and larger, the gain introduced by compression will increase as everything scales up. And this observation concludes my talk, such that when the models are getting so large, the gap between the compute and the bandwidth are becoming even larger. And with compression, you can convert a portion of compute into effective bandwidth, which becomes a trade that gives more and more benefit over time. And in short, the more you compress, the more you save. We envision future hardware AI accelerators to come with built-in codecs for tensors, such that they have a smarter approach to scale their bandwidth. And that being said, NVIDIA, you should be building more codecs. And that concludes my talk. Thank you for your attention, and I welcome any questions.
Any questions from audience? So I have one question. I mean, do you have any inference speed up gain using this codec?
That's a great question, because that comes back to our last sentence that NVIDIA should be building more codecs. So currently, because NVIDIA doesn't really have the demand for such high bandwidth video codecs, so in existing GPUs, we don't see any speed up, because the bandwidth, what's already available on GPUs, are pretty limited.
And then another question here is that the biggest challenge, by the way, I'm from Apple, and then already this is no information. Apple is using video codec to compress the LLM. So we are using that. The biggest challenge I see with the codec-based compression is that the streaming implementation is pretty tough with the video codec, because you need to stage a certain sufficiently large information first.
Yeah.
Because that's how video codec works. But if we use group quantization, those things, we can do streaming for every 64 numbers and so on. So do you envision that not being able to do streaming during the first time, it can be an even bigger challenge than do you follow my questions here?
I think there are a lot of things going on here. So first, for our method, we are still relying on 16-bit floating point computation. So the codec compressed format is only an intermediate format for saving the footprint space or saving the bandwidth. So we are still doing our computation on 16-bit. And I think in the future, definitely I would envision that future hardware to have their own codec design specifically targeting tensors rather than just videos. And with that format, they can resolve a lot of the drawbacks from existing video codecs.
Okay, fair enough. Thank you.
Thank you.
Yes, so right now, in consideration of the time limit, we might need to move forward to the third answer. Once again, thank you so much. Let us give applause.